All right, I think I'm recording. Let's take a look at some of these radical equations and see if going through the solution and explaining some things might help some students. And you kind of want to here really be aware that when you square things that exponents don't distribute. I'll point that out multiple times as we do these problems. So here I have a square root symbol. If we square both sides, that radical symbol will go away. So I'm going to come in and square the left-hand side, and to balance the equation, square the right-hand side. So the beginning of these problems are just like the ones from day one on the radical equations. So I've got x squared plus 5x is equal to 36. Now, this equation is a quadratic equation. If we solve and find the solution set, it will be the same solution set as the original equation. However, when we square both sides, we may have introduced extraneous solutions. We're going to have to check our answers into the original equation to see if they check. We know it'll be solutions to to this equation, but I'm trying to find the solution set to the original equation. For a quadratic equation, I could complete the square right now. That will always work. I can get it in standard form, subtract 36 from both sides, and do the quadratic formula. That will always work. But generally, we first try to factor, because if we can factor, it's just usually a shorter, faster solution. So if I can come up with two numbers that when multiplied together give me a negative 36, but when added together give me a positive 5, and I think that positive 9 and negative 4 will do the trick. So I'm not yet ready to say that negative 9 and positive 4 are my solution set. I'm ready to say that they're the only possible solutions here that I have. So I need to check each one of these into the original equation. So let's check x equals 9, or excuse me, negative 9. On the left-hand side, what do I get? Well, if I plug this in, if I square negative 9, hey, I get 81. And 5 times 9 is 45, but that will be subtraction. And is that 36? Well, yeah, 81 minus 45 is 36, and the square root of 36 is 6. And that's what they claimed. They claimed on the right-hand side. See, initially, I wasn't sure if I was going to get 6 or not, but now I know that I do. So, hey, that negative 9 does check. So let's plug in 4 and see if it checks. 4 squared is 16. 4 times 5 is 20. And 16 plus 20 is 36. And the square root of 36 is equal to 6, just like they claimed. So I'm fairly confident now that these two are both in my solution set, that both of those satisfy not only my new equation that it resulted from squaring, but the original equation. That was the solution set that we really wanted. All right. Yeah, we're still having internet problems and stuff, so I tried to pull up our homework online and I couldn't, so I found an extra copy on the back counter. So let's make sure, as I'm writing these down, I think I've mentioned it to a few classes that one of the silly mistakes that I do a lot is I copy the problem down wrong. So right away I'm doing a different problem than what's on the sheet. So hopefully I've copied this number 2 right. Let's take a look at it. I have on the left-hand side two terms. Terms are separated by addition and subtraction. Factors are separated with multiplication and division. This first term has my radical in it, and I want to get that by itself. So I need to move this other term to the other side by adding 6 to both sides of the equation. And I get 5 here. So if I now come in and to get rid of this radical, if I square the left-hand side and the right-hand side of the equation, I have balanced it. And when you square the radical, it goes away, and what we get is this, what's underneath, and 5 squared is 25. So I have a quadratic equation here. Let's get it in standard form. x squared plus 2x squared plus 5x minus 25. All right, so let's give myself some room. When you're factoring trinomials and the leading coefficient is 1, you'll find in general that it's easier if the leading coefficient's different than 1. Now, at least this is a small number and it's a prime number, so it's not going to be really all that difficult. We can probably do it real quickly in our head by trial and error, but let's be a little bit more organized. And the method that they use in the Algebra 1 team, if you're going to tutor, you may want to verify this with one of the previous algebra students or look back at your notes, or if you have younger brothers, sisters, cousins in Algebra 1 classes, just talk to them and find out how they're solving these. But I believe with this x method, I take the first term times the last term. I get negative 50x squared. Now the game begins. I'm trying to find two numbers whose product, whose multiplication, it multiplies together to give me the negative 50x squared, but yet added together gives me the positive 5x. So of these two numbers, I know the one larger in magnitude is going to be positive. So I believe that you can just, by trial and error, just in your head, play around with the values that have a product of negative 50, and you can see that 10 times the negative 5 is negative 50, and that 10 plus negative 5 is positive 5. So they then, I believe, they then have them place this information in a table, because they have seen tables before of when they multiply binomials together. So now, since we're factoring this trinomial into a product of binomials, we're going to work from the inside of the table outward. When you're multiplying binomials, you work on the outside of the table inward. So you're just going in the different direction. Along one diagonal, we put the first term and the last term from our x. That last term is negative 25. Now, it's not that those are interchangeable along that diagonal, and with the 10x and negative 5x, those are interchangeable along the other diagonal. All right, so we now look. I should have mentioned that I should always start by looking to see if there's a greatest common factor. With 2, 5, and negative 25, there was no greatest common factor. If there was, I need to factor that out before I come in and attempt this organization, this x method. The 10 and the negative 25, hey, 5 is common, and vertically here we can see a negative 5 will divide. X is not common to both, but negative 5 divides both of these values. If we look horizontally here, 2 and negative 5 are relatively prime with respect to each other, but there is a common factor of x. And if we look vertically here, they're both even numbers, and they both have a factor of x. So now, if I multiply the outside entries together, I should get the body of the table. X times 2x, 2x squared, negative 5 times x, negative 5x, 2x times 5, 10x, negative 5 times positive 5, negative 25. So we have our possible solutions pretty easily here now. It's seen that 2x minus 5, x plus 5 is equal to 0. So I'm going to move this other stuff kind of out of my way. Will it let me do that? Sometimes it does not cooperate, but today it is. All right, so we have a zero product theorem that says if you have two or more values, if you have a product of values that equals 0, at least one of these factors has to be 0, maybe more, maybe all of them, So either this 2x minus 5 is equal to 0, or this x plus 5 is, because if their product is 0, one of them has to be 0. Well, this is a two-step equation. You simply add 5 to both sides and then divide by 2. So I'm having one possible solution. At least it's a solution to this equation, but I don't know yet if it's a solution to my original equation. And then over here, negative 5. So, hey, let's bring up the calculator. And I can't believe that they have me turn on the virtual calculator. All right, On the left-hand side, what's underneath that radical, let's figure out what it is first. So I've got 2x squared, but x I believe to be this 5/2. And plus 5x. Alright, so that's what I'm going to be taking the square root of, and hey, I don't need a calculator for that. The square root of 25 is 5, and 5 minus 6 is -1. So this guy is checking. Now let's plug in a -5. On the left-hand side here, underneath the radical, what do I have? 2 times, well, I already know that -5 squared is 25. So I'm just going to put in, really I knew that 2 times 25 was 50. And now 5, let's go back. 5 times a -5, that's minus 25. So hey, I got 25, and the square root of 25 is 5. And 5 minus 6, this guy appears to check as well. So unless I've made a silly mistake in my check, which is very possible, I get these guys as my 2 solutions for number 2, so hopefully you're getting them as well. Now if you do notice an error in any of these videos and stuff, please speak up and say things, because your other classmates would definitely like to know that I could take a second look at it and double check and see if I agree with you, and then we'll try to make some pop-up or some insert into the video correcting any errors that I might make. Alright, now what do I do with that sheet? There it is. Number 3, moving right along. Number 3, 2 times this and minus 2. On the left-hand side, I have 2 terms. The first term has 2 factors, and one of those factors is a radical. I want to get that by itself. So I have 3x plus 6, and I'm going to move this to the other side, so then if I add 2 to both sides, I'll have x plus 2. Now, a few students have said, hey, don't we divide this by 2 to get the radical completely by itself? And you could, but then over here, you're working with a 1/2 x plus 1, and you're just about to square that. If I were you, I would leave that factor alone right there. See, we need to isolate the term that contains the radical, but I can square this probably easier than I can if I move, if I divide by 2 and if I introduce a 1/2 on the right hand side. Now, you do have to remember that what this, to square something, means this base repeated, that we have this times itself. So in multiplication, we can, change the order, that we can multiply the 2 times 2 first. So my point is, don't forget to square the coefficient there, the number that's in front. The radical goes away. Now over here, this is not x squared plus 2 squared, and you're going to have somebody that accidentally does that. If you FOIL it out, however you learn to multiply binomials together, do that. If you do it in the body of it using table or the word FOIL or some type of other pattern, all of those patterns are just ways that teachers are trying to illustrate the mathematical property that's called the distributive property. So I have a quadratic equation here. I have in one variable x, and the biggest exponent on x is 2. That's how, and when we say that we have a second degree equation, or we say that we have a quadratic equation, and we want to get it in standard form, we want to get this equal to 0. They're either going to call it standard form or maybe refer to it as a general form. So I only have an x squared term there, but I do have an x term there and there. If I'm moving everything to the right hand side, this will be minus 8x. If I'm moving the constant term to the right hand side, that'll be minus 20. So I believe that factors to x minus 10 and x plus 2. And it is awfully easy to get those signs backwards, to have x plus 10 and minus 2. But if you look, since the last term is negative, they need to be opposite in sign. Since the middle term is negative, the larger in magnitude has to be negative. So hopefully that helps. So possible solutions, or at least solutions to this equation, are 10 and negative 2. Now, that might not be the same solution set as our original equation, because when we square both sides of the equation, we introduce the possibility of extra solutions that they call extraneous to the original equation. So let's check that. 10 on both sides. 3 times 10 is 30, plus 6 is 36. Square root of 36 is 6. So I have 2 times 6 minus 2. 12 minus 2, I have 10 over here. And this x on the right hand side, we have a 10. So hey, it checks, because originally we weren't sure if we would get 10 or not, But on the right hand side, that says equal x. X is 10. Hey, that checks. Now let's check a negative 2. All right. On the left hand side, oops, I erased the x equals negative 2. On the left hand side, if I plug in a negative 2, that's a negative 6, and a negative 6 and positive 6 are 0. And the square root of 0 is 0, and 2 times 0 is 0. So I have 0 minus 2, and 0 minus 2 is equal to negative 2. So that checks. I believe that both of these should be in my solution set. The fourth one. And here we have the dreaded 2 radicals in the same equation. And two radicals in the same equation are okay if right here, instead of adding 2, you were just adding 0. If this were the problem, now it's incorrect to say the radicals cancel each other, but that's how you guys describe it. You're actually squaring each side, and it's through properties of exponents that radical goes away, or if you want to call it properties of radicals. It's not correct to say that they cancel, but I know that that's how students describe things. We have this additional term plus 2, so it's not quite as easy as it would be if that 2 was not there. We isolate one of the radicals. Well, by isolate, we get that term by itself. So on the left-hand side, all I have is a radical. Hey, I'm ready to square both sides of this equation. So let's take a look at what we have. On the left-hand side, it's fairly easy. When you square that radical goes away, and you just have the 2x plus 1. But on the right-hand side, when you square this, some students may have to do some scratch work here. What you get is x plus 1, and then you get 2 radical x, but you got to double that, so 4x plus 1 plus 4. Now, if that's too quick, or you don't want to do that in your head yet, one organized way is through a table, and to say that I've got one term being the square root of x plus 1, and my other term is 2, and for the other binomial, it's the same thing. It's a repeated multiplication, a squared binomial. The radical times the radical goes away, and we're just left with x plus 1. When we multiply it by 2, we have 2 of these radicals. And here we're multiplying it by 2 again, and we have 2 of those radicals. And 2 times 2 is 4. And along this diagonal, I got 2 of these radicals, 2 more, for a total of 4 of them. So that's where that 4 came from. So in a sense, I'm just doing this table in my head when I square this out. All right. Let's shrink this up, move it up here. Now, originally, our problem had two radicals. There was one here, and there was also one here. But by squaring this, we now have just a single radical there. So at first it may not seem like it's getting simpler, but it actually is. We need to get this term by itself, all right? So maybe first, so that you don't do too many steps at once and make any silly mistakes, the x is going to be there. I'll put a 1. 1 plus 4, hey, that's going to be 5. And then I have this 4 times radical x plus 1. So these two terms I need to get on the other side because what am I doing? I'm trying to isolate the radical. I need to get that term by itself. So I have x. If I take away x from each side, if I take away 5 from each side, I get x minus 4 is equal to 4 times this expression. Now, to get rid of that radical, we square both sides of the equation. Again, if you want to divide by 4 and work with a 1/4 x minus 1, you can do it. But I'm going to keep that 4 there and square it because I'm not going to try to do a lot of arithmetic with a fraction like 1/4 in there. It's not impossible. It's just, to me, more difficult than what it needs to be. If I square this left-hand side, x squared minus 8x plus 16. If I square the right-hand side, 16, oops, the radical would go away, times x plus 1. So I have a quadratic equation here. I need to get this in standard form and then either factor or apply the quadratic formula. So maybe it's not looking quite as bad as it did originally. All right, I didn't want to record my yawning, so it's bad, I guess, if I'm boring myself, but really it's just because I'm tired. Hopefully you find this helpful. All right, so quadratic equation, I'm trying to get this in standard form. I've got x squared if I subtract 16x from each side, minus 24. Hey, now when I subtract these 16s, they just cancel. All right, so remember, right now, technically, we squared. We don't know if we introduced extra solutions when we squared it. So let's factor this to x times x minus 24, and let's see if both of these check. We get x equals 0 and x equals 24 as possible solutions. So if I come over here to do my check, if I plug in 0 on the left-hand side, 2 times 0 is 0. 0 plus 1 is 1. The square root of 1 is 1. And over here, if I plug in 0, the question is, will we get the same value? Here I get the square root of 1, which is 1, and 1 plus 2, hey, that's 3. I don't think this 0 checks in our solution. If I've made a silly error, you'll have to tell me, but I don't believe that's in my solution set. So let's check this 24. If I double 24, I get 48, and if I add 1 to it, I get 49. 49 is a perfect square. When you take the square root of 49, you get 7. Now, the question is, on the right-hand side, we've got 24 plus 1. Hey, that's 25. And the square root of 25 is 5, and 5 plus 2 is 7. So this one checks. I believe our solution set only has 24 in it, that this x equals 0 was an extraneous solution, an extra solution. All right, so let's keep going. Number 5. Lucky number 5. No, I don't know if it's lucky or not. Okay, we're back to one that, like the other day, I don't have two radicals. It looks pretty straightforward. If I square the left-hand side, I've got to square the right-hand side. So I get 7x plus 8 because the radical went away. is equal to x squared. So if I move these two terms to the other side, now if I attempt to factor this trinomial, I get x minus 8 and x plus 1. That looks good. Possible solutions of 8 and of negative 1. Well, let's check 8. We've got 7 times 8, 56, plus 8, 64. Square root of 64 is 8. 8 equals 8. That one does check. Plug in a negative 1. So that'll make that negative 7, plus that'll be 1. But the principal square root of 1 is never going to equal a negative number. So this guy does not check. This is extraneous. And really, I guess if I would have started with the right-hand side, you got a principal square root could never equal negative 1. So I didn't even need to bother plugging it in on the left-hand side to see what it evaluates to, because on the right-hand side, this number will always be 0 or positive, because this is a principal square root. It wants you to take the positive square root of the number. So x equals 8 is my only solution for problem 5. For the next problem, for problem 6, well, what do we have? We have this radical x minus x is equal to 3 radical x. All right, we have on the left-hand side, we have two terms. One of those terms has a radical. On the right-hand side, we have a single term, and it contains a radical. This term that has the radical is by itself, so I can jump in right away and square both sides of this equation. So if I square the left-hand side to balance the equation, I have to square the right-hand side. Now, this guy over here, like I say, if you have to do this multiplication in a table, if you have to spell out the word FOIL, multiply the first terms, the outside terms, the inside terms, and the last terms, do it. However you feel comfortable with getting this product, you should do. All right, on the right-hand side, it's a little bit simpler. Don't forget to square the 3, and I get just 9x. Well, I have a new equation. Some people might argue, well, that's not simpler than the original one. Well, yeah, it is, because I had 2 radicals here, and now I only have a single radical there. I only have, that term. This is the only term that has the radical in it. So I need to get that by itself. So let's do that. Let's keep the negative 2x, radical x, right where it is. And if I subtract the x squared term, and if I take another x away, that'll be plus 8x. All right. Yeah, now this one of the classes asked me about this one, and I probably should double check and think about this a little bit more. Remember that we've been talking about extraneous solutions, that if you multiply both sides of an equation by x, or if you square both sides of an equation, you're introducing possible extraneous solutions. Well, we see that we have a common factor of x here. You know what? I know how I can describe this. Let's get this equal to 0. Okay, so let's move this x squared term to the other side. Let's move this 8x to the other side. Let's keep this term here. Okay. So now every term has a factor of x. This factors to x times x minus 8 minus 2 radical x. That doesn't look very much like an x, does it? Okay. And now we have a zero product theorem. This is the way I should have described it in class. I didn't think of it till just now. See, I was afraid to divide both sides. When you multiply both sides by a variable, you sometimes introduce an extra solution. Well, but you can easily discover that by checking your work, and if it doesn't check, you throw it out. But if you divide both sides of an equation by a variable, you'll sometimes lose a solution, and that, discovering that you've lost a solution and what that solution is can be much more challenging than just checking your answer. But see, if I do it this way, if I write it in standard form and now I write it in factored form, this splits into two equations, one that's x equal to 0 and one that has this equation that has a radical term in it that I need to get this radical term now by itself and square each side. So I know that 0 is in my solution. And a quick inspection, I can see that satisfies the original equation. The square root of 0 is 0, and 0 minus 0 is 0. And 3 times the square root of 0 is 0. So I know that that's going to check. I know I needed to get that in the solution, and I want to be careful that if I would have canceled an x, if I would have divided both sides by x, then you may not have written down that 0 is in your solution set. So it was better for me to use this zero product theorem than to divide both sides by a variable. I should have thought of that in class, and I apologize that I didn't. All right, so let's get this radical by itself. We've got x minus 8. If I simply move that to the other side, and like I say, I'm not going to divide by 2 and then work with a 1/2 on the left-hand side. When I now square both sides of this equation, I'm just going to have to remember that I square the 2. I don't want to make a silly arithmetic error. So I've got x squared, I have a binomial squared. So, thinking back of your completing the square, it should be no surprise that this trinomial, if you take half of negative 16 as negative 8 and you square it, 64, that this factored to x minus 8 quantity squared. You're just going in the reverse order when you multiply it all out. Like I say, don't forget to square the 2 and the radical goes away. So far all of this work has led to this trinomial, and one that I can easily factor. I've got x minus 4 and an x minus 16. Negative 4 times the negative 16 is positive 64, and when you add them together you get the negative 20. So I get a possible solution of 4 or 16. I don't know if one of these is going to be extraneous or not. We come back up to the original equation, and on the left-hand side, I have the square root of 4, which is 2, and 2 minus 4 is a negative number. Well, right away, warning signs are going off, so let's write that out. On the left-hand side, square root of 4 minus 4. And the question is, will this simplify, will this evaluate to the same number that's on the right-hand side? Well, on the right-hand side, we have 3 times 2. On the right-hand side, we have 6. But over here, 2 minus 4, we've got a negative 2. Those are not equal to each other. This is extraneous solution. It does not satisfy my original equation. It satisfies one of the other equations, especially this last one here, where we got rid of that radical. Now let's check the 16. Maybe it is in the original solution set. So if I take the square root of 16 minus 16, the question is, will that equal 3 times the square root? Well, this guy is 4 minus 16, negative 12. And over here, 3 times 4 is a positive 12. No, those are not equal, so this is extraneous. So my answer for number 6 is a no solution. I can't remember if I got that in class or not, so if you end up listening to these videos and stuff, maybe mention it, that because I struggled a little bit today. I didn't get enough sleep last night, and I was making some errors all day long, And maybe you're the same way. The day of a test or the day of a quiz the night before, maybe you don't want to stay up too late. Get a good night's rest. All right. What do we have for number 7? I am just dying to know. I'm going to probably do this in 2 parts. Take a break for a minute and, post this video and then do the rest in the second part of it, if you don't mind. All right, so I have an equation with 2 radicals. One of the radicals is already by itself. There's no advantage that I know of to truly, well, I guess there is an advantage. I would leave it like it is because it'll be easier for me, I think, to square the right-hand side than it would be if I had that, if I had a minus 1 over here. So I'm going to leave it as is. I take that back. This is probably going to be an easier way to solve this, as opposed if they had a minus 1 over here. All right, because when I square this, the radical goes away, and when I square this, I have x plus 2 of these radical x's plus 1. So now I want to get this term that contains that radical by itself. So I've got a 1x there. If I take x away from both sides, I have that. And this one, if I take 1 away, I have minus 15. So, yeah, it results in something that's not that bad. I went from originally having 2 radicals in my equation to now having just a single radical, and I have that radical, the term that contains that radical, I have it by itself. All right, so let's square both sides of this equation to get that. And each time that we're squaring these, we're introducing the possibility of extraneous solutions. You have to remember, you got to check your answers. You got to check your work with the original equation. So I've got x squared minus 30x plus 225. And you're going to laugh at me because I'm going to double check and make sure. Yeah, 225. All right. Don't forget to square that 2, and the radical goes away. So now get this in standard form. X squared minus 34x plus 225 is equal to 0. So let's see if we can factor this before we jump in and try to use the quadratic formula. If we can't factor it, then we'll play with the quadratic formula. Now, what I always do, people don't believe me. I'm not very good at arithmetic. 225 we know was 15 squared. And 15 has factors of 3 and 5. So I've got 3 times 3 and times 5 times 5. That 9 times 25 is 225. Now, with this last term being positive and this middle negative, I know that I'm going to be multiplying 2 negative numbers together. Okay, so I need to figure out how can I do this and get a sum of 34. Well, I think if I just take the negative 20, if I take a negative 9 times a negative 25, the product will be positive that I wanted, that 225. But when you add these together, you'll get the negative 34. So we stumbled upon it. There it is. So x minus 9, x minus 25. All right, so by the zero product theorem, if we have a product that's equal to 0, then one or more of the factors must equal 0. This x minus 9 has to equal 0, or this x minus 25 does. Well, I normally don't put this step in because you guys can just look at that and say, hey, if x is 9, 9 minus 9 gives you 0, and then 0 times anything. And this guy, if it's equal to 25. But I'm not saying those are my answers yet. I'm saying those are the possible solutions, the possible answers. We have to check it in the original equation. Let's see. Because I am more tired than normal, I am going to use my favorite calculator here online. On the left-hand side, what's underneath that radical? Well, 2 times 9, I guess I don't need the calculator. 2 times 9 is 18, and 18 minus 14 is 4, and the square root of 4 is 2. So on the left-hand side, when I plug that in, I'm getting a 2. Now on the right-hand side, will I also get a 2? No, because square root of 9 is 3, and 3 plus 1, 4. So I don't believe this guy checks. Did I do that right? Yeah, 18 minus 4. I don't think that guy checks. Let's check this 25. 50, 36, 50 minus 14, 36. Square root of 36 is 6. On the right-hand side, square root of 25 is 5, and 5 plus 1 is also 6. I'm getting that this guy checks, but the other guy didn't. I believe that the only solution to problem number 7 is that x equals 25. This x equals 9 was extraneous. X will not equal 9. I don't know why on that one solution, on the other day's solution set, I put x not equal to 9. And there maybe I just should have made the comment, note that this is extraneous. That's what I intended. That's what I was trying to imply, but I don't think I did a very good job implying it with those mathematical symbols of not equal to. All right, let's I am going to stop here, call this part 1, and finish part 2 a little bit later after I take a break. But it'll feel like I've been right back if you start the next video.